The last section of this chapter is about Fourier transform. I think from the experience we obtained in the previous section, that Fourier cosine transform and Fourier sine transform, even though their transform format is the same as their inverse transform, but you can see that both are correlated to each other. For example, in here, when we derive some properties about Fourier cosine transform, then it will relate to Fourier sine transform. On the other hand, if we derive some property about the Fourier sine transform, it will relate to the Fourier cosine transform. So they have. And also, you can see that there is something strange, right? Occurred when you derive some properties. So it is tempting that can we combine Fourier cosine transform and sine transform together? Okay, and then end up with a very nice transformation, and everything, the properties is very symmetric and just smooth. And the other thing is that then we can go to complex variable field, because we have a beautiful theory of function of one complex variable, and we will talk about that later. And so we can use the results we have in complex analysis prior to Fourier series analysis or Fourier analysis in general. So here is the way we will do, right? So in this section, all right, we will derive a complex transform which is very useful in science and engineering. Okay, so once again we assume that F is an absolutely integrable function on the whole real line. So now we go to the function over the whole real line, which is piecewise, which is piecewise continuous, right? Which is piecewise continuous on any finite subinterval of the whole real line, and has the left-hand derivative and the right-hand derivative at every point in the whole real line. Okay, so we just like we studied in the section of Fourier integral theorem. Now, by the Fourier integral theorem, right? So by the Okay, by the theorem. Okay, we have the average of the left-hand and right-hand limits of the function f can be expressed by an integral aw cosine of x plus bw sine of x. Okay, up to w for all. So this is true for all x, right? And we know this integral may need to be interpreted as improper integral. Okay, so all right, and we know AW is equal to 1 over pi of this integral cosine x, okay, and the BW is 1 over pi sine, okay, and all gradient W gradient equal to 0. Okay, so this is the result from the Fourier integral theorem. Okay, so we have that. This is in general. It is true for any function f which is absolutely integrable on the real line, which is piecewise continuous on any finite subinterval of the whole real line, and f has the left-hand derivative and the right-hand derivative at every point. Okay, so we have that specification. We have this is very strong result. You know, this is a difficult result actually. We go to this result through a journey that is not easy, right? So we get that, and now we want to turn this format into some nice form. Okay, so now we are going to another journey, all right, to replace this integral into a nice form. Okay, now so the first step is substituting. So let's say this is the 11. Okay, and this one is 11.9.2. Okay, so substitution the AW and BW into here, into the integral. Okay. Alright, we go back a little bit when we deal with the Differential theorem, right? We derived the Differential theorem to here, but we go back a little bit. We have. Okay, so let me run it. Alright, so this is the average, okay? Now the average is equal to 1 over pi from 0 to infinity. So, and this f of u cosine u cosine of x plus sine of u sine of x du and dw. Okay. So we just do the substitution, go back to there. So we have a double integral here. Right. Remember, actually, we go to here and then go to there, right? When we derive the Fourier integral theorem. And Okay, and all we know, this one, so we have cosine w x minus u du dw. Okay, so combined together, this is equal to cosine w x minus u. Okay, x minus u here. Okay, and we have that. Now, begin with our journey. Look at this one. It's a function. It's a function of what? Of w. Because we fix x, all right? Now, so this is a function of w. That's why we integrate this function of w over w. And when it's a function of w, because cosine is even, so this one is an even function of w. Right? It's an even function of w. So, and we integrate this function from 0 to infinity. Now we can extend the other way, right? Without changing. Okay? But we have to what? Put one half, right? So we have to put that. Yes. Okay, so now become more and more symmetry, right? The double integral will be the same. This is the first thing we have. All right, now, once that, then, so observation from that, it prompts us to an observation that if we consider sine function, okay, sine function, we replace the cosine with sine. Then it's a function of w, but it's an odd function. Okay, so it's an odd function of w. And so if we integrate over all the w, sine should be equal to 0. So this is 0. Any questions? It's not a magic, it's just a truth. Okay? Just a truth. Any questions? Okay. Now, all right, so now we just add, because this double integral is 0, right? So we add this to here. So now, the same thing, the average. Okay? Pi here. Okay, we add something I. This is the imaginary unit times okay. It's pretty sad, right? We add this step because this integral has value 0. but then it become, so now we will join, so this becomes 2. Okay, so we now join them together. And here, this is exponential function of decentralized function by Euler's formula. Okay, this is from Euler's formula. The exponential function, and exponential one always a nice function. Okay, and so we have. So now we have 1 over 2 pi Fu I exponential I W x minus U dU dW. Okay, U and dW here. Okay, and now we will split this integral. First of all, we split the factor, right? This factor. And exponential function is pretty good because that we have the sum rule. Okay, so we have that, and here we have right. So now we have something that f of x can go over this transform to a function of the w, and then you go over another transform to get back to the f of x. Alright, so this gives us, so this integral, the integral here altogether is called the complex Fourier integral. Right? So this is called the complex Fourier integral, compared with the real Fourier integral we obtained in section 11.7. Okay? So this is the complex. The only thing we add is this term. This term. So so now we define the Fourier transform of a function f defined on the real line is defined to be here fk w is defined to be 1 over square root of pi f of x e minus I of x dx for all right will exist. Okay, so we define the integral in inner parts of this double integral to be the Fourier transform of f of x, okay, And we'll sometimes just write f of f. Okay, f means Fourier transform f of f. Okay, so this is f of f. Also notation. Okay, and now we will state the existence of Fourier transform as a theorem, and we will also categorize some of the properties of Fourier transform. Okay, this is the first theorem in the textbook, but my version is contain more information. Okay, so if f is an absolutely integrable function on the whole real line, then its Fourier transform exists. Okay, exists means that we get a function which is defined over all the real line here, right? Because this is should be true for all W in the real line. Alright, so the first statement. Furthermore, okay, FA is uniformly continuous. So it's not only continuous but also uniformly continuous on the whole real line. And we have the value of the Fourier transform as W goes to plus minus infinity, okay, is equal to 0. This is basically the Riemann of Bayes lemma. Okay, look at here. Maybe okay. Probably. I try to prove for this theorem, okay, to show you why it is uniformly continuous. Okay, but I will actually mention that remember this is okay. So this is cosine okay. And as we know, cosine actually is cosine plus sine. Okay. So as W goes to infinity, as the frequency goes to infinity, by Riemann of Bayes lemma, is go to 0. Okay? Also, this is go to 0. Okay? So that it goes to 0 plus I plus 0 as infinity. Okay? So you can actually by the Riemann okay, so this part is a consequence of the Riemann, the big Riemann. Okay, but the Fourier transform is uniformly continuous, need a proof. So I write a proof. Okay, yeah. The existence of the Fourier transform is obvious from that f is absolute integral. Okay, so we know some information about the Fourier transform. We know the Fourier transform is very smooth. Means it's smooth because it's uniform continuous, and it goes to 0. So basically, if we write down so it's just like something like if we take the absolute value, okay, you can see that it is go to 0 and it's uniformly continuous, okay, on the whole real line. So this is the property of Fourier transform. So it's a nice function. Okay, and now we are able to reveal this identity here. Okay, this means something. So from the Fourier integral theorem, we have the existence. Actually, this is the existence of inverse Fourier transform. So the importance of Fourier integral theorem is that it gives you the existence of inverse Fourier transform. Because to have the Fourier transform is not a big deal, right? Very easy to know that you will have Fourier transform if f is absolutely integrable. But to have the inverse transform, okay, it's very difficult. It's very difficult. But we already have a good result from the Fourier integral theorem. So is that f absolutely integrable on the whole real line. Okay, and fk, the Fourier transform of f. Okay, if f is piecewise continuous, okay, if it's on any finite subinterval of the real line, and as the left hand derivative and the right hand derivative at every point in the real line, then f of x is equal to 1 square root of 2 pi. The Fourier transform of f times ei of x dw. Okay? This is true for all x in the real line, but except at points x0 where f is discontinuous. Okay? And there, for any discontinuity point, the value of the integral, okay, equal the average. Okay. Ninth theorem. Okay, and so as before, the right hand side will be denoted as the inverse transform, the inverse Fourier transform of FA. Okay? So so actually, from our previous theorem, because inverse Fourier transform and Fourier transform basically are the same, except if you say the phasor. For Fourier transform, the phasor you use is e to the minus I of x. But here, the phasor used is e to the I of x. So actually, pretty much they are the same. Okay? So this one is always 1. This one always is a times property. Okay? For example, it is okay. Now, so this theorem, this existence theorem require a lot, right? About f. So f should be, other than it is absolutely integrable, it should be piecewise continuous on any finite interval, and has a left-hand derivative and right-hand derivative at every point. All right? Yeah. Now I give you another version. All right? Another version of the existence of the inverse Fourier transform. Okay, so if f and its Fourier transform fa are absolutely integrable over the whole real line. Then, now, if f is absolutely integrable and its Fourier transform is also absolutely integrable. Okay. If f is absolutely integrable, we know its Fourier transform exists, right? And then we know that the Fourier transform is uniformly continuous and very nice, vanish at infinity. But it does not guarantee that FA is absolutely integrable. You can find counterexample, many counterexamples, right? Show that FA is not absolutely integrable. But If in case fa is absolutely integrable together with f, if we have this situation, then the original function will equal to the inverse Fourier transform for almost all okay, for almost all. So this is true. The existence of inverse Fourier transform is because fa is absolutely integrable. Okay. So when fa is absolutely integrable, of course the inverse Fourier transform, because this is absolutely integrable, so this transform exists. So this is exists. Okay? And this one is a function of x defined on the whole real line. And then this function will be equal to the original function f of x for almost all. So we know they are equal almost all. If in addition, okay, f is continuous, okay, on the real line, then f of x equal to the inverse, okay, for all x. Okay. One further addition. If f is continuous, if we know f is continuous, then they are equal for all x, not almost all, for every x. Okay. So you can have that. So this version somehow is more general than this version. But this version requires the inverse, the Fourier transform of fa is absolutely integrable. Okay. And here you do not need this condition, but you need the other condition about f over f. Okay, over f. Any questions? Of course, Fourier transform is linear. Okay, so Fg, they are absolutely integrable. AB, a constant. Then f plus bg is absolutely integrable, and the Fourier transform of af plus bg is equal to the a of Fourier transform plus b times the Fourier transform of g. Okay. So we have linearity. Alright, and similarly, Rayleigh theorem is about the Fourier transform of derivative. Okay? We have Fourier cosine transform of derivative and the Fourier sine transform of derivative. Now, we have Fourier transform of derivative. So now we require f to be continuous. Okay, the interval is 1, and f of x goes to 0 as f the value of x goes to infinity, so it decay. And the third thing is that the Fourier transform exists. Okay, so the Fourier transform exists, right? 1 to 3. So f and f prime, the derivative is that which is piecewise continuous. Alright, this continuous on every finite subinterval, the whole real line. Okay, so with that, of course you can have a stronger condition as I said before, as fx. So this is implied phi f is absolutely integrable over R. Okay? So if f is absolutely equal, of course the Fourier transform exists. But I will just let it open, that say, okay, its Fourier transform exists. Let it open. Okay, so if that, then we have the formula. The Fourier transform of f prime exists, of course, and is equal to I W, the Fourier transform of f. Very clean, right? So that we have this nice formula. We have this nice formula. Alright, and I also give a proof in my supplement, so I will skip that. And for the rest of the time, in this class, I would like to talk about convolution, an important operation in functions. So now, definition. The convolution denoted by f star g of two functions f and g on the whole real line at a point x in the whole real line is defined to be, so the convolution at a point is going to be the integral f of p and gx minus p dx. And if this integral exists, you can show very easily by change of value for that. Alright, we can exchange the argument here. It's very simple, just by change of variable. So if the integral exists, if it exists. Okay, this is the convolution. So convolution is an operation that so if we have f of x here, and if we have another function so it says p, so this is gp. Okay, now that this one actually is equal to g minus p minus x. Okay. All right. So first of all, you shift. For example, if x is 1. So you shift that, then you may be Okay, so this is G, P minus X. Okay, you shift. Okay, and then you reverse that. So you reverse that, it's that okay, so this is G minus P minus X. And you take the product and integrate everything. This is called convolution. Okay. This is called convolution. And convolution is an important concept when you consider linear system. So you will take a course called sigma systems, and in that course you will see convolution is very important. Okay, very, very important in that here. Okay, so this is convolution. Right? Mathematically, this is just definition. Okay, so this is a procedure and how you make the integral, the convolution. So at each x, you have to take the shift, right, of the g function first, and then you take the image relative to the y-axis. And then you multiply with these two together, and then you integrate over them. Okay, so this is the convolution. Now, I have to, once I define something, because this is when it exists, right? So I have to state the existence of convolution. And the existence has been, so if f and g, right? So if f and g are absolutely integrable on the whole real line. Okay, suppose that. Now then we have one, the convolution, right? The convolution exists for almost all points in the real line. Okay, it's not guaranteed for every point, even though f and g are absolutely integrable. So f and g are absolutely integrable. Guarantee only that the convolution exists for almost all x. But that is good enough. Okay? For almost all. For almost all. Second, so this convolution can be regarded as a function defined on the real line almost all everywhere. Okay? And so that the convolution as a function itself is absolutely integrable. Very interesting. Okay? So the convolution itself is absolutely integrable. And we can measure right? The integral of the x value will be less than or equal to the product of the absolute integral of f and the g. Okay, so we have this result. Third, if in addition, okay, if in addition either f or g is bounded. Alright, suppose either f or g is bounded. Okay, on R then the convolution exists for all x in R. Okay? So one more condition guaranteed that the convolution exists for all R, for all x in R, not only for almost, this time for almost. And is bounded on R. Okay? First thing, if in addition, right? If in addition, the bounded function f our g is continuous on R, then the convolution is also continuous on R. Okay, so now the convolution becomes a very good, nice function. Okay. So you add one by one, right? Add one by one, add more and more conditions, and you get more and more good properties about the convolution. So initially, if f and g are just absolutely integrable over the whole real line, then the convolution exists for almost all points in the real line. But that is good enough to say that this convolution can define a function on the whole real line, and this function is absolutely integrable. Because for integration, points, the value in the length, which is equal to 0, will be negligible because they are all zeros. Okay, and so we can see that it's upper bounded by the product of these two integrals. If f and one of the f or g is bounded, then convolution exists for all points. Okay, and is bounded. Furthermore, if the bounded function f or g is continuous, then the convolution will exist for all points in the real line and is bounded and continuous. Okay, nice property. Okay. Okay. Last theorem. The convolution theorem of Fourier transform. F, G are absolutely integrable on the whole real line. So when f and g are absolutely integrable, then we know the convolution defined on the whole real line almost everywhere. And it is absolutely integrable. When it is absolutely integrable, the convolution has Fourier transform. Okay? So the Fourier transform of the convolution, right? The Fourier transform of the convolution is equal to a factor square root of 2 pi times the Fourier transform of x and the Fourier transform of g. Very nice property here. Okay? So we have that. This is so the famous convolution theorem of Fourier transform. Okay. And I tried to give a proof of this convolution theorem by using Fubini's theorem. And actually, I run out of my time. Okay, and maybe I say a little bit. We need Fini theorem. Let me say it very simply. How do we so we let f(x1) be a function, right? Defined on a Cartesian product of two intervals and j. Now, if you test the f value, you test the f value, okay, test, and then you integrate, right? Do it. You integrate over y first and then over x first, and you find that this is finite. Or you do it the other way. You integrate over x first, and then over y second, and you find it's finite. If either one is true, then true. Then you have you can then we know either one true. Then we know that then first is that these two actually are the same. Is equal to okay. So basically, either one is finite, then they are the same. The second thing is more useful. Without the absolute value sign, you can exchange the order of integration. That is the forbidding theorem. Very useful version. Of course, you have different version of the forbidding theorem, but this is the most useful one. Okay. So whenever you evaluate the double integral, but you need to change the order, how do you know that it is valid for you to change the order? Well, very simple. Take the actual value and try to integrate either this way or this way, and find, because either way will be easier to do the integration, okay? In many situations. And you find either way is finite, then everything is okay. And that is the basic principle. Okay? That is the forbidding theorem. Very useful theorem. We use that in science and engineering all the way, but we didn't mention why. Okay? But this is the reason. Okay, so that is for today's lecture. Okay.